We will now learn about the last design pattern for the course, the visitor design pattern, which is highly related to the composite design pattern that we spoke about last week. As usual, let's take a look at the learning objectives. So number one, we're going to see what the motivating problem is for the visitor design pattern, which is about processing the recursive system. If you recall from last week, the building or constructing a recursive system is the design problem for the composite design pattern. So that's why I said these two design patterns are really highly related. So we'll speak about their relationship in just a moment. So number two, since the two design patterns are so highly related, so our first design attempt is to simply just give to you a very straightforward extension to the composite design pattern in order to solve the processing of recursive system problem. And then we'll see that that particular straightforward extension is going to unfortunately violate two design principles, cohesion and also single choice principle. We'll speak about it. And then from there, we'll introduce to you another design principle called open-close principle. And once we learn about this new design principle, we'll introduce to you the second design attempt, which is the commonly used visitor design pattern. And then we'll talk about architecture, we'll talk about implementation, clients versus supplier, and also we'll talk about at the runtime there is a special phenomenon called the double dispatch for the visitor design pattern. So that'll be the flow for this lecture. Okay, so now let's first of all talk about the motivating problem for the visitor design pattern, about processing recursive system. Before that, let me present to you a slightly different problem. Remember when we talk about the composite design pattern, we spoke about computer equipment, or we spoke about the furniture. So now let's consider another similar problem that's also recursive. Let's say based on the composite design pattern you learned from last week, design classes to model structures like architecture, right, of arithmetic expressions. So let's make the following assumption. For the base cases, you can see in the green, you got basically just integers. And then for recursive cases, let's say you got addition only. Okay, we may extend the kinds of operators maybe later, but for now, that will be what you have to deal with. Okay, and notice that the expressions over here can also be recursive. For example, you might say 341 plus 2 plus 5. So that could be as complicated as you like, but only addition is supported, just for simplicity. Okay, so now think about how you would use your composite design pattern to actually draw a solution for this particular problem over here. Okay, pause the video and think about it before I show you the solution. Alright, so hopefully you had a chance to think about how to apply the composite design pattern for building recursive arithmetic expressions. So this will be one possible solution. It's a design architecture. Let's go over that quickly, and you will see they share similarity with what you learned previously. Let's now start from the top. At the top, we define a general concept about expression. And over here, we got actually both base cases and also recursive cases. But for each one of them, we only got one instance. So for example, you can see for the base case, we got constant over here. So this will be the base case, right? Let me just annotate this. So this will be the base case. And also on the right hand side, for addition, apparently it's really the recursive case for building arbitrarily complicated arithmetic expressions. So this will be recursive. Okay, so this will be addition over here. And then, so this will be for recursive case. Okay, so, and then we got this for satisfying the single choice principle, because we might have multiple instantiations of similar recursive structure. In that case, we can really reuse the composite class. So over here, let me just highlight it over here. So this will be the composite, right? So the composite over here, I'm doing something slightly different from what we did before. So here, rather than having an array or list of child expressions, I simply got left and right. You can think about this as a composite for just a binary expression. But you know, it's just an illustration over here. what you could have done is you can simply say you want to have children of type an array of expression, and then you can have the associated invariant to say the size of the children's list should be no more than 2 or exactly 2. Okay, let me just write it down over here. Alternatively, you can simply say composite okay, it's should be deferred, and then you can simply say children, and then it's going to be, for example, a list of expression. I'll just say exp for short. Okay, and then of course this is a class. Okay, composite. Okay, and then we may have just an invariance over here. Okay, and then we say children. Okay, the count should be maybe exactly 2 for the binary expression. If you want to make it a little bit more general, you can fix the constraint over here. But just to show you, you got different alternative to actually present your class. Okay, so that's about the composite design pattern we have. Oh, one more thing to note, which is also very important. You can see we got the idea about multiple inheritance, the design idea. So you can see the addition is both an expression over here, and also is a composite, right? So now let's think about 2 questions over here just to conclude this quick review on the composite design pattern. So question number 1. How do we construct a composite object representing 341 plus 2 based on the architecture over here, right? That's something we spoke about in the previous topic for composite. So this one should be quite straightforward. You can see how do we basically have to create 341. We had to create a constant 2, and then we had to create an object for addition, and then we need to add this object here as a left child and add this object here as a right child. Let's write it down quickly. So assuming that every effective class over here has their constructor called make. Let's make the assumption. So what we can do is we can say let's declare first. You can say constant 1 and also constant 2 should be both of type constants. Okay, of type constant over here. And then we got also addition. Let me just call it add. Should be of type addition. Okay, you can see addition over here. And let's now create the 2 constant objects. So we can say creates c1 dot make. So now for, let's assume that the make constructor is going to take the value you want to create, which will be 341. And we can also do creates, and then we say c2 dot make, and then it's going to be 2. All right, and then let's also make the assumption that for the addition over here, the make constructor is going to take exactly 2 arguments, which will initialize the left and right. So what you can do is you can say creates over here, and then we're going to say add dot make, and then we should pass the left and right, and the left will just be c1 and the right will be c2. So let's visualize what's going to happen at the runtime just for completeness. So what's going to happen is at the runtime we're going to have a variable called add, and that one there is going to point to simply an object of type add, and then the add, it inherits the 2 attributes left and right from the composite. So it's going to be L for left, R for right, and then left is actually going to point to some objects of type constants, and the constant is simply going to have the attribute from here which is value. So the value is going to be 341. Okay, and then the right is also, I'm just running out of space, but you can think about the right is also going to point to another object over here of type constants, and the value will be 2. All right, but you can think about the value over here as we learn. It's like a price routine that we learned in the previous lecture about composite. You can think about, I'm putting here just 331 and also 2. It's like a private attribute that we store, and then whenever you call value, which is a routine that will be effective in the constant and in addition. And in this, for the base case, they're going to return 2 and also 341 respectively, right? That would make sense. Okay, and then, of course, now if you try to do the following, if you try to say, if I say at dot value, is very similar to when we say chassis dot price is going to add up the prices for all the components, right? So that one there is going to return, apparently it's going to add up 341 and 2, so that'd be 343. And we talk about how you can trace such recursive call previously in the lecture, so I'm going to omit that part. So this is about the check for the first question, right? Hopefully you're comfortable with that. Let's talk about the second question here, which is also interesting to answer. How would you extend the design to include, let's say, another base case called variables, and also another recursive case called subtraction? How would we do that? Okay, so the variables here will be very easy, right? Let's just try that. So we want to extend just another inheritance, so I'll simply put it here. Let's say another inheritance arrow over here, and then it's simply just going to be another base case. I'll just put it here, over here, just another class. And then it's going to be variable. I'll just call it var. Okay, also effective. So the new base case will be easy. So what about over here? What about subtraction? So here you got two options over here. So currently we simply got addition over here. You might be wondering what we had in the previous lecture for the composite. There is actually an intermediate class called composite, maybe composite expression, like a composite equipment or composite furniture. But we didn't have that over here. So let me show you what it would look like without it, and then tell you, and then convince you why it'll be better to really have the intermediate class back. So let's say how we can do subtraction over here. So apparently I can simply put subtraction over here. Okay, so I can say plus and then subtraction, and then I'm gonna have multiple inheritance as well. You can see one arrow over here and also one arrow over here. So basically, every time you want to have a new class representing a new recursive case, you always have to create a circle for the class and also two arrows for the inheritance. But this may not be very desirable because it's going to make your diagrams too messy as we add more classes, for realistic expression language. So what should we do instead? So what we can do instead, let me just draw a fresh diagram in the next slide over here. So let's now remember. Okay, let me just copy this one over here just to save some drawing over here. Just make it quick. So now, how can we add that particular composite? So what we can do is, you can think about we're just going to rename this particular class over here as composite expression. So you may want to make it composite expression. Okay, so this will be deferred, let's say, and then the composite over here, you may just want to make it generic, right? Maybe the left and right over here, you can simply just be maybe T, for example, right? And also you can have maybe set left, set right, and etc. And now the composite expression over here is going to say inherits composite, and then over here we're going to instantiate the type T by expression, right? So this something we also talk about. It's worth reviewing. So now how can we add some recursive classes? So now every time if you want to add a new class for the recursive case, all you got to do is to simply create a class, and over here, for example, you got addition. And how many arrows do we need? You can see as opposed to adding two arrows over here individually, we just need one arrow. That's all we need. So we're going to say addition is going to inherit from the composite expression. And also we can have another recursive case over here. Let's call that subtraction. And this is also going to inherit from the composite expression. Okay, and of course, you don't forget, you also got the variables over here. So now it will look very similar to what you had for last week. So that will be the variable. All right, so hopefully you're feeling comfortable about using the composite design pattern. It's really important foundation in order for you to appreciate how we're going to build later on for the extension for visitor. All right, so that's about this one here. Okay, let me go back to the slides. So now here is the motivating problem. So the previous one is simply just help you to really brush up with your memory about the composite design pattern. So now let's see the real design challenge for us. So the design challenge is we want to extend the composite pattern to support operations, various operations actually, such as evaluate, which we did already, but in addition to it, we want to do pretty printing, either to print prefix or to print postfix, and we want to do type checking. So these are the very common operation you would like to do given some expression language. Think about we are given some programming language and we want to build a language processor for that. Okay, let me illustrate a little bit more closely about what I really meant by the various operation. So this is the object structure, the composite object structure that we built using the composite design pattern. That's what we are given. And now, given this particular object over here, the object reference add, we would like to do the various operation. We want to do, for example, evaluates, and evaluates is pretty much like a value that we defined previously. So the evaluates, for example, evaluate is simply just going to just return. So it's going to be 341 plus 2. So it's going to be 343. So this will be the output from evaluates. So what about pretty printing? So let's say if we want to do the pretty printing for the prefix notation, so the output should be something like we're going to put the operator first and then the operands next. So it'll be 3 and then 343. So this might be something you have seen in your data structure course, right? Like how you can manipulate the printing of your string. And also the next one, let's say we want to print the postfix notation, in which case we're just going to reverse the order. We're going to do the operands first, and then we want to do the operator last, right? You can see it's a similar operation, but not exactly the same, but just with different outputs. So finally, so for type checking, in this case, since we only support either constants and also addition, right? In this case, if you got 3 plus 343, apparently it's a valid operation. In that case, it would just be, for example, just true from type checking. So whenever the type checking result is false, so that means you're going to have some compilation error. It's basically what your language compiler will do for you. So what would be one case where the type checking result should be false? For example, the constant over here, it could be for both Boolean constants and also integer constant. For example, if you try to check, type check, let's say 343 and then plus another constant, but it's not a Boolean constant. For example, you say false. Apparently, this is going to be not type correct. So this is just a very simple language structure over here. I mean, a very simple composite objects, and also the number of base and also recursive cases are just very minimum. Just for illustration, but I can think about realistically, if you're given a language with a complexity like IFO, Java, or Python, in that case, doing the type checking is definitely not trivial. It's actually quite a challenging task to do. So that's something we would like to really solve at the design level. We want to solve it properly using the proper pattern. So that's the motivation here, one of the motivations. So now, having understood about what every individual operation is going to do, so now how can we extend the composite design pattern? So this is the composite design pattern. How can we support these 4 operations? So let me start with what you know already. You can think about the value over here. So what we learned from the previous lecture about the composite. So this would be maybe defer query, for example. And then every effective descending class, they should actually implement it. So that'll be value returning integer. So that should be implemented in the base case. And also the value over here will be integer, also implemented, right? So we also trace about how such recursive routine can be executed at runtime. So that would be for the evaluation. So evaluation is now covered. So now let's say we want to support also pretty printing for the prefix. So now how can we support it? the most straightforward solution would be, why don't we just put in the same way? So why don't we say print and also prefix, and then that one is going to return a string, for example. And at the top level, we simply don't know how to do it just yet, so that's why it's deferred. And then for each of the effective descendant classes, we're going to increment it. So this will be prefix in the base case. So that'll be effective, and also we're going to say print prefix. That's also going to be returning a string. All right. And similarly, what about printing the postfix? Well, we put it in the same class. That's why I say it's a straightforward extension to the composite design pattern. But whether or not it's it's really an extension with a good design, especially does it satisfy the common design principle? We'll discuss that in just a moment. So print postfix, and also string. And then let me just be complete. Let me write it down. So this kind of simulates the order of your implementation, right? When you actually want to implement this particular design. So that'll be postfix, and then you'll be a string, and this will be print postfix, which will return a string. All right. Finally, also this particular type checking over here. Although type checking is not so related to pretty printing, but since we are following the straightforward extension, let's just do it. So that means I just write in other space. I'm going to write outside the box. So it's going to be type check, and then that one is going to return the boolean, or just a bool, and then it's deferred. And then we're going to implement that. So let's say type checking. So type check over here, returning bool, and it should be implemented. And also for another effective descendant classes, we'll say type check, returning boolean, and also it's effective. So now you can see that the reason that I'm using different colors for every operation is because somehow you can argue that each of the operation, they don't really share the same nature. You can argue that, for example, well, basically what I'm trying to say is we want to think about the flaws of this particular design. So I will give you one hint over here, and then we'll discuss it. All right, you may want to pause the video and think about the following two design principles that we kept emphasizing in the course. One is cohesion. Another one is single choice principle. Let me use another color. So single choice principle. Can you actually think about how should this design be judged with respect to cohesion and with respect to single choice principle? Okay, pause the video and think about it. All right, assuming that you have thought about it, let's first talk about cohesion. So this is why I try to maybe write every operation over here in a different color. It is because somehow they are not that similar, even though they're all functions or operation that's supposed to be done for expression. But if you look a little bit more closely, the nature of each operation is not really the same. For example, if you look at, let's say we talk about cohesion, right? Let me just give you one example. If you think about type checking over here and also print prefix, how are these two operations related to each other? Really, they are not related. So this will be, so you can think about these two operations, for example, they are not so related. Not related, but put in the same class. So this implies violation of cohesion. So whenever you're trying to judge for cohesion, you're really judging for individual classes. Think about all the features, try to compare them pairwise, and see if they really should belong to the same class. Apparently, you can see this is only for printing in a particular way, but this one is about systematic analysis of the expression to see if the expressions can be added together or put together, by applying the operator. So these two are definitely not related to each other. Also, you can see print postfix and also type check are also not really cohesive, right? And also you can think about evaluate and also type check also are not very related to each other. And also evaluate and printing also are not really related to each other, right? You can see my point over here. So putting all the operations in a single place is not necessarily good always. Let me put it another way. We want to think about if you try to put all the operations into this particular class, effectively you're moving towards a Superman module. Okay, you can think about this guy over here is really very close to a Superman module because you're putting everything that you really want to implement into a single class without thinking about decomposing them into different modules for modularity. All right. So typically, if you actually don't really follow cohesion, one of the possible consequences is that you have a Superman module. All right. So that's about cohesion, right? Cohesion is not really satisfied for this design. So what about single choice principle? Single choice principle means every time if you want to modify, introduce a change, then there should be only one place or the minimum number of places that you make the change. For example, let's say we want to, let's make a very simple example. Let's say we want to change the way we print out prefix. Let's say rather than simply printing that, we simply, so this is a prefix notation over here. And then we simply just want to change the way we put it. For example, we may want to put it like this. We may want to say plus, and then followed by maybe 3 with brackets, and then 343. Let's say for the second number, we simply want to bracket in a different way. Just for example, let's say we just want to modify that. So what's the consequence of that? The consequence of that is by changing this, you have to change in every effective descendant classes about how the change should be implemented, which means you're going to change this routine over here. You also got to change this routine over here, depending on how many effective descendant classes you have. If you got n effective descendant classes, you got to modify n places, not just a single one. So this violates single choice principle. Okay, so that means any change you want to introduce is going to affect all descendant classes. So it's actually multiple places you have to let me just use a different color. So there's multiple places you have to implement a change. So that definitely violates this the single choice principle. All right, so that's about the flaw of this particular design, which is kind of straightforward and maybe intuitive to you, but it's actually quite a poor design. So that's why we really want to have a much more elegant design, and this will be the visitor pattern. But before the visitor pattern, we would like to talk about one more design principle, which is called the open-close principle.